Today we will talk about quantization of electric charge, starting with Robert Millikan's oil drop experiment, uh, using the known electric field and the values of the gravity and mass. Millikan and Fletcher were able to determine the charge on oil droplets until they reach mechanical equilibrium. Let's see how this happened. First, let's introduce the apparatus of Robert Millikan. We have a battery or a source of electric energy that's connected to a switch. This is a switch. It's open now, so there's no flow of electric charges or electric current. We have an eyepiece, a telescopic eyepiece to observe what happens inside. We have an oil atomizer with a cathode on the nozzle. So when oil is sprayed through the nozzle, it will pass through the cathode and the particles will be negatively charged. You will see this in the next slide, as you see. So when oil was sprayed from this atomizer through the nozzle, it passed through this blue part, which is the cathode, that resulted in negatively charged oil droplets. The oil droplets there will start falling down due to gravity until one of them or some of them they pass through this tiny hole. It is a very tiny hole and it starts going down. When we observe this, we have to turn on the source of electric energy, so we close the switch. The current will start flowing. This results in charging this plate, the upper one, positively, and the lower one is negatively charged. So now if we look at this oil droplet that is negatively charged, it experiences an electric force upward due to the electric field, and there's the force of gravity downwards. We keep adjusting the strength of the electric field, which means in turns that we're adjusting the electric force until this droplet reaches a state of equilibrium. Mechanical equilibrium means that the forces acting on the object are balanced. If the forces are balanced, it means that the force of gravity is equal to the electric force applied on the oil droplet. So the force of gravity is mass multiplied by gravity. This one is QE, the charge multiplied by the electric field. So if we want to calculate Q will be equal to mg over E. Every time Robert Millikan did the calculations, he found Q to be a multiple of a fundamental value. Which is 1.6 times 10 to the power of negative 19 coulombs. So let's assume he did the experiment the first time and he found a value for Q. Let's call it Q1. The second time, another value for Q. The third time, another value, a different value for Q. Let's take values. Let's assume this was 6.4 times 10 to the power of negative 17 coulombs. This was, let's say, negative 3.2 times 10 to the power of negative 19 coulombs. We will have, let's assume, 4 times 10 to the power of negative 12 coulombs. Okay, if you divide any of those values of Q1 or Q2 or Q3 by 1.6 10 to the power of negative 19, you will get a fixed value, a whole integer, a whole number by negative 1.6 10 to the power of negative 19. This led Millikan to think this way. He said that then the smallest amount of a charge that exists in nature is this value. So this is the value that he concluded to exist as the smallest amount of a charge in nature. Then we got to know that the charge of an electron, which is E minus, which is equal to minus E. So negative 1.6 times 10 to the power of negative 19 coulombs. The charge of a proton, which is P plus, is plus E. So it is plus 1.6 times 10 to the power of negative 19 coulombs. Quantization of a charge implies that a charge can assume only certain discrete values. Let's make it simple. The charge is measured as an integer multiple of the elementary charge E. So when we say Q equals NE, let's do this. Okay, when we use Q equals NE, N can be 1, 2, 3, 1 million, 1 trillion, and so on. N cannot be a decimal or a fraction that does not result in a whole number. Okay, so it is a positive whole number. Let's solve an exercise to see how we work or how we use quantization of electric charge in a simple way. Is the charge Q equals 2 times 10 to the power negative 20 coulombs existing in nature? Does it exist in nature? Let's see. Okay. I will use Q equals NE. Q is 2 times 10 to the power of negative 20 is equal to N multiplied by 1.6 10 to the power of negative 19. So N is equal to, divide both sides by 1.6 10 to the power of negative 19. We get for N 0.125. This is not an integer. Okay, so I will say therefore Q equals 2 times 10 to the power of negative 20, so negative 20 coulombs does not exist in nature. Let's take another example. If we have this charge 0.5 10 to the power negative 14, does it exist in nature? We will do the same thing. Q equals N E. 0.5 times 10 to the power of negative 14 equals N into 1.6 times 10 to the power of negative 19. So N is equal to 0.5 times 10 to the power of negative 14 divided by 1.6 10 to the power of negative 19. This results in 31250. Is this a whole number? Yes, it is a whole number. So Q, which is 0.5 times 10 to the power of negative 14 coulombs, exists in nature. Now, just to clarify the idea for you to not to get confused between Q and N. Q can be a decimal as long as N is a whole number. Okay, so Q can be a decimal. As you see, it's 0.5 10 to the power of negative 14. It is a decimal. It is not a whole number. Okay, while n should be a whole number. So n should be a whole number or an integer.